The evolution of galaxies in modern cosmology is understood as a prolonged and continuous process, where matter gradually transforms from simpler forms of structuring to more complex ones. This does not constitute a sequence of separate events, clearly delineated in time. Rather, it concerns a gradual change of states, occurring within the limits of fundamental physical laws. Galaxies do not emerge as ready-made structures and do not preserve a constant appearance. They form, transform, and age, reacting to environmental conditions and their own internal dynamics. Initial conditions for galaxy evolution are laid even at early stages of universe existence. After a period in which matter was almost homogeneously distributed, there appear small density fluctuations. These deviations were very small, but exactly they determined the subsequent course of events. In regions with slightly elevated density, gravity began acting more effectively, gradually attracting surrounding matter. Over time, these areas became increasingly more massive and more complex in structure. Dark matter plays in this process a key role. It does not emit light and does not interact with electromagnetic radiation in the usual sense, but creates a gravitational framework in which subsequently accumulates ordinary or baryonic matter. Exactly in potential wells of dark matter begins concentrating gas, from which form the first stars. Without this invisible component, the evolution of galaxies in the form known to us would be impossible. At early stages, galaxies had no clearly defined shape. They were irregular clusters of gas and young stars, which constantly changed their structure. Processes of gas cooling, star formation, and feedback influence of these stars on the surrounding medium occurred simultaneously and interrelated ly. Massive stars quickly completed their existence, enriching the interstellar medium with heavier elements and changing conditions for subsequent generations. It is important to emphasize that galaxy evolution is not linear. It does not move from simple to complex in a direct sense. At different epochs dominate different processes. At certain stages, the key role is played by mass accumulation. At others, redistribution of already existing matter. A galaxy can change shape without changing significantly the total mass, or conversely, significantly increase mass without sharp structural rebuilding. One of the central concepts in studying galaxy evolution is the balance between gravity and internal processes. Gravity seeks to gather matter together, whereas energy, which is released during star formation and stellar death, can disperse gas and slow further growth. This balance is never static. It constantly changes in time, and differently is realized in galaxies of different mass and environment. A galaxy's shape is the result of this balance. Disk structures arise where gas retains significant angular momentum and can organize into a rotating system. More spherical or elliptical structures form in environments where matter motion becomes less ordered, often due to interactions and mergers. However, none of these shapes is final. They can change under the influence of both internal and external factors. The scientific community does not interpret galaxy evolution as a standard path, identical for all formations. Conversely, each cluster possesses an individual biography, determined by starting parameters and subsequent phenomena. However, in this diversity are distinguished general tendencies. Exactly, they enable formulation about universal evolution mechanisms, not limiting them to strict norms. Studies of distant galaxies provide the opportunity to look into the past. Radiation from such formations travels to us extremely long, and we observe them in a form which corresponds to the initial periods of the cosmos. Comparing these data with characteristics of nearby galaxies, research strives to reconstruct a generalized scheme of transformations. However, this reconstruction constantly remains mediated. It is based on numbers, concepts, and hypotheses, which can be adjusted with time. Mathematical concepts of galaxy evolution constitute a key tool, but they do not provide final conclusions. In such concepts, it is necessary to account for the colossal multitude of phenomena, which occur at different levels, from movement of individual luminaries to kinetics of enormous matter streams. Each simplification affects the conclusion. Therefore, various concepts can differently represent the same observable characteristics. In contemporary research, a significant place is occupied by understanding the limits of cognition. Certain aspects of galaxy evolution are explained quite convincingly. Others are the subject of disputes. Particularly, processes, which determine the rate of star formation in different classes of galaxies, have not yet received a universal interpretation. Similarly, open is the question regarding the precise function of invisible matter in creating small elements of architecture. In quiet contemplation, galaxy evolution can be imagined as an extremely slow process, practically invisible in short temporal intervals. Galaxies do not transform suddenly. They slowly move from one regime to the next, preserving at this internal organization. This phenomenon has no clearly defined start or ending. It constitutes a component of the general chronicle of the cosmos, in which each cluster occupies its own position. Therefore, galaxy evolution appears as a prolonged interconnection between substance, force, and space. This is not a chronicle of cataclysms and fractures, but a chronicle of accumulation and redistribution. Comprehension of this enables perceiving galaxies not as motionless objects, but as living, in the scientific understanding systems, which transform at a pace significantly slower than all human notions regarding time. The emergence of primordial galaxies constitutes one of the most complex and simultaneously the least directly measurable periods of cosmic transformation. Research does not possess the ability to observe this phenomenon in details. Understanding about it is formed on the basis of mediated investigations of distant objects, study of relic signal, and mathematical modeling. All these data sources complement each other. However, none of them provides an exhaustive and complete scheme. Since when in potential depressions of invisible matter began concentrating gas, there appeared preconditions for formation of primordial luminaries. This gas possessed an extremely elementary chemical composition. It almost entirely was formed from hydrogen and helium with a negligible admixture of lighter elements. The absence of heavier elements substantially determined the physics of cooling. Gas released heat less productively than in subsequent periods, and because of this, the first luminaries according to contemporary notions were more massive than luminaries, which form in galaxies nowadays. The emergence of initial stellar formations did not proceed in a stable environment. Gravitational wells had not yet reached significant depth, and gas flows remained inconstant. Newly formed galaxies regularly lost a certain fraction of their matter through the influence of energy, which released giant stars. Radiation and stellar streams heated gas, and outbursts at the end of existence of similar stars were capable of pushing it beyond the limits of gravitational retention. This indicated that galaxy evolution at initial stages was uneven and intermittent. Initial galaxies substantially differed from the known spiral or elliptical formations to us. They were more compressed, less regulated, and frequently had a chaotic shape. Their structure continuously transformed in response to gas inflow, internal phenomena, and interactions with surrounding objects. At this moment, boundaries between separate galaxies were less pronounced than in the contemporary cosmos. Star creation in initial galaxies probably occurred in compressed but powerful episodes. After gathering sufficient gas mass, there emerged conditions for rapid star birth. However, the feedback effect of these stars on surroundings could quickly stop the further process. In the result, the galaxy transitioned into a phase of relative calm, until again it gathered gas. Such a regime substantially differs from the more stable star formation in many contemporary galaxies. Special significance for early galaxy evolution had the saturation of interstellar space with heavier elements. After the death of first stars, gas was no longer chemically primordial. Even a small presence of heavier elements drastically changed its characteristics. Cooling became more effective, which facilitated formation of less massive stars and more complex stellar systems. This transition was not instantaneous. It occurred gradually and differently in different regions of the universe. Formation of stellar clusters in early galaxies probably occurred under different conditions than in later epochs. High gas density and rapid dynamic processes facilitated formation of compact systems. A portion of them could survive to contemporary time in the form of ancient globular clusters. However, the direct connection between these objects and the first stellar systems is not fully proven and remains the subject of scientific discussions. Early galaxies did not exist in isolation. They formed in an environment where interactions and mergers were significantly more widespread than today. Small galaxies could quickly unite, forming larger systems. In this process, stars, gas, and dark matter redistributed, changing the structure of future galaxies. Such a hierarchical growth model well agrees with many observations, but does not explain all details without exception. Simultaneously, there exist alternative approaches which attempt to emphasize the role of internal processes in forming early galaxies. In these models, the main emphasis is placed not on mergers but on continuous gas inflow from the surrounding medium. Both approaches are not mutually exclusive. Contemporary notions allow that the evolution of first galaxies was determined by a combination of external and internal factors. Studies of distant galaxies allowed distinguishing only the brightest objects of past epochs. This causes bias in observational data. Less massive and dimmer galaxies of the primordial cosmos find themselves beyond the possibilities of direct study. Therefore, any conclusions regarding typical characteristics of the most ancient galaxies must consider this limitation and cannot be considered final. In general, understanding the very first galaxies can be imagined as unstable yet filled with potential systems. They did not yet have a defined shape and prolonged equilibrium. However, exactly in this instability formed conditions for subsequent complication of cosmos structure. Gradual accumulation of changes, even in a disorderly environment, created the foundation for future ordering. Therefore, the most ancient galaxies were not a completed result, but rather an initial stage of a prolonged path. Their evolution was determined by limited resources, powerful stellar feedback, and constant interactions. Exactly from these conditions, gradually formed more stable and diverse galactic systems, which are observed in the cosmos today. One of the key mechanisms of galaxy evolution in contemporary cosmology is considered the merging process. Under this approach, galaxies are not viewed as isolated systems that form once and then only slowly change. On the contrary, they are the result of multiple unification of smaller structures into larger ones. Such a scenario is called hierarchical because it presumes sequential growth of complexity and mass of galactic systems. In early cosmos, mergers occurred significantly more frequently than in the contemporary epoch. Space was more compact, matter density higher, and distances between young galaxies smaller. Under these conditions, gravitational interactions quickly led to convergence and subsequent unification of systems. Mergers did not always have a symmetric character. Often it concerned the absorption by a large galaxy of a significantly smaller satellite. The merging process is not instantaneous. It unfolds over prolonged time and passes through several phases. At the initial stage, galaxies begin experiencing tidal influence on each other. Their stellar disks deform. Extended structures and streams appear. Subsequently, systems lose orbital energy and transition into a phase of closer interaction, which concludes with the formation of a unified gravitationally bound object. Consequences of mergers for the internal structure of galaxies can be very different. During merger of two disk galaxies with comparable masses, the ordered motion of stars can be substantially disrupted. As a result, forms a system with a less pronounced disk and more spherical shape. Such events are viewed as one of the paths of elliptical galaxy formation. However, this scenario is not universal and depends on many parameters, including disk orientation and gas content. Less massive mergers, during which the satellite mass is significantly smaller than the mass of the main galaxy, usually do not destroy its general structure. They lead to gradual halo growth, appearance of stellar streams, and local disturbances in the disk. Exactly such events are considered typical for prolonged evolution of large galaxies and calmer epochs. Gas plays a special role in merger processes. During gravitational interaction, galactic gas components can lose angular momentum and move into central regions. This creates conditions for elevated star formation activity. In certain cases, there arise short-lived yet intense bursts, which substantially change the internal state of the system. However, not all mergers are accompanied by such phenomena. If the gas supply is limited, the effect can be weak. Hierarchical growth does not mean continuous chaos. Between episodes of active mergers, galaxies can remain in a relatively stable state for very prolonged time. During these periods, internal processes dominate, such as slow disk rebuilding or stellar population evolution. Therefore, mergers are important, but not the only factors of evolution. Scientific models of hierarchical growth agree well with many observations of large-scale universe structure. The distribution of galaxies, their mass function, and characteristics of dark matter halos confirm the concept of sequential buildup. However, at small scales arise discrepancies between theories and facts. Particularly, the number of predicted small satellites does not always agree with observations. This demonstrates modeling imperfection or the significance of phenomena which are still insufficiently accounted for. There exist other views on the significance of mergers in galaxy evolution. Certain studies emphasize the importance of stable gas inflow from extragalactic space. In similar models, galaxies can evolve without regular mergers, maintaining disk-like structure throughout a prolonged period. Contemporary concepts assume simultaneity of both processes, while their comparative influence depends on galaxy mass and cosmological era. From the perspective of an observer, signs of past mergers are not always evident. Gradually, stellar streams disperse, stellar trajectories mix, and the initial event geometry is lost. Only careful analysis of kinematics and chemical characteristics of stellar groups enables recognition of these signs. Even under such conditions, interpretation can be controversial. In contemplative understanding, hierarchical galaxy buildup can be imagined as gradual superposition of the past. Each merger creates an imprint, but does not dominate over all the rest. A contemporary galaxy constitutes a combination of numerous events, distributed in time, among which occurred prolonged phases of relative stability. Therefore, galaxy mergers constitute a significant yet not sole evolution factor. They determine general buildup directions and transformation. However, the specific image of each galaxy is created as a result of multi-component interaction of numerous processes. Understanding this enables viewing galactic evolution not as a sequence of sharp transformations, but as a continuous and multi-level process where changes accumulate gradually. Besides mergers and external interactions, galaxy evolution is substantially controlled by internal processes. These processes do not depend on fresh matter inflow from outside or on sharp gravitational disturbances. They arise inside the galaxy itself and develop slowly, practically imperceptibly, over limited time intervals. Exactly such internal evolution creates a significant portion of galactic form diversity which is observed in the cosmos. One of the leading mechanisms of internal rebuilding is stellar disk dynamics. The disk is not a rigid or motionless structure. It is formed from billions of stars, each of which moves along its own orbit in the general gravitational field. Minor deviations in motion of individual elements can gradually accumulate and lead to emergence of large structural characteristics such as spiral arms or bars. Spiral structures in disk galaxies are not permanent formations. They are viewed as waves of enhanced density which slowly propagate through the disk. Stars and gas penetrate these zones but do not remain there for long. Such a concept explains why spiral arms can persist throughout great time, even when individual stars change their location. However, the detailed essence of these waves and conditions of their stability remain the object of scientific investigations. Bars are yet another example of internal rebuilding. These are elongated stellar structures which form in central parts of numerous disk galaxies. Their emergence is connected with dynamic disk instability. A bar can effectively redistribute angular momentum among different galaxy parts. As a result, gas can slowly move toward the center direction, changing conditions in internal regions. This matter redistribution creates long-lasting consequences. Gas inflow in central regions can facilitate formation of compact stellar structures or change star formation rate. Simultaneously, outer disk parts can lose part of gas and become less active. All this occurs without sharp events and is not accompanied by large-scale disturbances, but gradually changes the galaxy appearance. Internal evolution affects also the disk vertical structure. Gradually, stellar orbits can become less flat. The disk gradually thickens. This phenomenon is connected with accumulation of small gravitational disturbances, especially with interaction with molecular clouds and spiral waves. As a result, forms a complex multi-layered structure where different age populations of stars occupy different vertical levels. The galaxy bulge also can form or change as a result of internal processes. In certain scenarios, the bulge is not a merger result but arises gradually from disk material. Such a bulge type has different dynamic and chemical properties than bulges formed as a result of past mergers. Distinguishing these scenarios is complex and requires detailed stellar population analysis. Gas plays a special role in internal evolution. Its ability to lose energy and cool enables it to react to gravitational disturbances and change spatial distribution. Thanks to gas, internal structures can influence star formation rate, creating feedback between dynamics and chemical galaxy evolution. However, this influence intensity depends on gas quantity and conditions in a specific system. It is important to emphasize that internal processes do not act separately from external ones. Even weak interactions with other galaxies or with intergalactic space can change internal dynamics. However, during prolonged periods without significant mergers, exactly internal evolution determines main changes in galaxy structure. Scientific models of internal galaxy rebuilding are based on combining analytical approaches and numerical simulations. These models demonstrate that even in the absence of external influences, a galaxy is not a static system. It constantly changes, although these changes occur slowly and without sharp transitions. However, precise timescales and details of these processes depend on initial conditions and remain the object of refinement. In contemplative perception, internal galaxy evolution can be imagined as quiet rebuilding, which occurs in background mode. Externally, the galaxy seems stable and unchanging. Only in long-term perspective does it become noticeable that its shape, star, and gas distribution have undergone changes. This slowness is a characteristic feature of most galactic processes. Therefore, internal evolution mechanisms complement the role of mergers and external interactions. They ensure smooth transition between states and allow galaxies to change without destroying general structure. Exactly thanks to such processes, galactic evolution acquires features of continuity and gradualness, which are defining for its understanding. The star formation process is one of the main mechanisms through which galaxies change their internal state. It is not uniform in time and space. At different epochs and in different galaxy types, star formation can be intensive or almost imperceptible. Exactly this non-uniformity determines a significant portion of galactic property diversity which is observed in the cosmos. Stars form in cold and dense interstellar gas regions. For this, it is necessary that gas could efficiently lose energy and compress under the action of its own gravity. The presence of heavier elements and dust substantially facilitates this process because they promote cooling. Therefore, star formation conditions transform with time in the process of chemical galaxy evolution. Primordial galaxies and contemporary systems are characterized by different star birth potentials. Stellar formation never encompasses the entire galaxy uniformly. Even in galaxies with high overall activity, there are present regions where the process almost does not occur. In disk galaxies, young stars usually concentrate in spiral structures or ring regions. In elliptical galaxies, conversely, contemporary star formation is insignificant or absent. These differences are the consequence of both initial conditions and subsequent evolution. A substantial aspect is that stars not only form from gas but also actively affect it. Massive stars emit an enormous quantity of energy and create powerful stellar winds. This influence changes temperature, density, and gas motion in the surrounding medium. In some cases, it can destroy molecular clouds and stop further stellar formation in a local region. The final stage of massive star life also has significant influence. After completion of nuclear reactions in their cores occur rapid rebuildings which lead to ejection of matter and energy into interstellar medium. These events enrich gas with heavier elements and create shock waves. The influence of such processes can be both destructive and stimulating for further star formation, depending on medium conditions. The feedback influence of stars on gas is viewed as one of the key regulators of galaxy evolution. Without this mechanism, galaxies could very quickly transform all available gas into stars. Observations show that this does not occur. Even in galaxies with intensive star formation, the process continues significantly longer than simple estimates based on gas freefall. This indicates the existence of effective self-regulation mechanisms. The feedback influence role depends on galaxy mass. In small galaxies, energy which stars release can be sufficient for ejecting a significant gas portion beyond system limits. This leads to subsequent activity reduction and forms galaxies with a small star quantity. In more massive galaxies, the gravitational field is stronger and gas usually remains bound with the system, although its distribution and state can substantially change. Star formation influences also observable galaxy properties. Young stars determine brightness in short-wave ranges, whereas old stellar populations dominate in long-wave radiation. Star formation rate transformation with time leads to gradual changes in galaxy colors and spectra. Exactly by these signs, astronomers classify galaxies and attempt to reconstruct their history. Simultaneously, it should be noted that no feedback influence model is universal. Different galaxies demonstrate different ratios between energy which stars release and interstellar medium reaction. This depends on system geometry, gas content, magnetic field presence, and many other factors. Therefore, science works with generalized descriptions which do not always reflect all details of specific cases. Against a calm background of galaxy evolution, stellar formation can be perceived as a pulsating yet restrained process. It is not a continuous flow and is not a chaotic explosion. This is a series of episodes distributed in space and time which together form the general rhythm of galaxy life. Thus, star formation and stellar feedback influence are an inseparable part of galaxy evolution. They do not determine all aspects of changes, but set frameworks within which galaxies can grow, age, and change their properties. Exactly through this interconnection between gas and stars, galactic evolution acquires the character of slow, self-regulated transformation. In centers of most massive galaxies are located supermassive compact objects whose mass significantly exceeds individual stellar mass. Their presence is established not by direct observation but through analysis of stellar and gas motion in central regions. The influence of these objects on galaxy evolution is not constant and identical in time. It manifests in the form of elevated activity episodes which can substantially change surrounding medium state. Galactic nucleus activity is connected with the accretion process. Matter which enters the central object gravitational field does not fall directly inside. It forms a rotating structure in which occurs gradual angular momentum redistribution. In this process is released energy which radiates in a wide range of wavelengths. Exactly this radiation makes active nuclei among the brightest sources in the universe. It is important to understand that the active phase is not a prolonged state. For its maintenance is necessary continuous matter inflow into the central region. If this inflow stops or decreases, activity weakens. Most of the time galactic nuclei remain in a calm state and almost do not manifest themselves in observations. Exactly, therefore active nuclei should not be perceived as a permanent galaxy characteristic. Active nuclei influence on galaxy evolution consists not only in radiation. Particle and energy flows which exit from central regions can interact with interstellar gas. In some cases, this influence leads to gas heating and reduction of its capability for forming new stars. In others, it can compress gas in certain regions, changing spatial star formation distribution. This influence character depends on many factors, and there is no universal description. In massive galaxies, the role of active nuclei can be especially significant. Observation shows that in such systems, star formation rates with time decrease. One of the possible explanations is exactly the central source energetic influence which hinders gas cooling. However, this mechanism is not the only possible one. Alternative models emphasize the role of gas supply depletion or surrounding medium condition changes. There exists correlation between central compact object mass and galaxy properties overall. Particularly, this object mass is connected with bulge characteristics. This connection indicates common central region and entire galaxy evolution. However, causal relationships in this case are not unambiguously established. It is unknown whether the central object determines galaxy development or both components form under common factor influence. Active nuclei play a role also in cosmic history at large scales. In the early universe, they were significantly more widespread than today. This indicates that accretion conditions in that period were more favorable. High gas density and frequent interactions between galaxies created opportunities for central region feeding. With time, these conditions changed and activity decreased. Scientific understanding of active nuclei role remains incomplete. Models differently evaluate feedback influence effectiveness and its duration. Some observations indicate strong influence on interstellar medium, others about relatively local effect character. This means that active nuclei cannot be viewed as a universal evolution regulator for all galaxies. In quiet reflection, active nuclei can be imagined as hidden energy centers which most of the time remain calm. Their activity arises and fades, not disrupting general universe equilibrium. They are not a constant source of changes, but in certain epochs can play a noticeable role in energy and matter redistribution. Thus, active galactic nuclei are an important but not dominating evolution element. They interact with the galaxy within complex feedback system limits. Their influence depends on mass, medium, and cosmic epoch. Exactly this dependence makes the active nuclei topic one of the most dynamic and open in contemporary galaxy evolution research. Galaxy evolution is determined not only by their internal properties or merger histories. An important role is played by the medium in which a galaxy remains throughout its existence. This medium is formed by universe large-scale structure, a system of filaments, nodes, and voids within which matter is distributed. Galaxy position in this structure affects its growth rates, gas availability, and interaction character with other systems. At large scales, galaxies are not distributed randomly. They form clusters, groups, and extended chains separated by large regions with low matter density. In such voids, galaxies are usually isolated and experience minimal external influence. In clusters, conversely, they remain in dense medium, where gravitational and hydrodynamic interactions are significantly more intensive. Galaxies in clusters evolve differently than isolated systems. High galaxy density leads to frequent close passages which can disturb disk structure and change gas motion. Besides, intergalactic space in clusters is filled with hot, rarefied gas. Galaxy motion through this medium can lead to loss of its own gas. This process gradually deprives the galaxy of resource for new star formation. In less dense galaxy groups, conditions are different. Here, interactions occur more rarely and usually have milder character. However, exactly in such groups often occur galaxy mergers with comparable masses. Low relative velocities facilitate gravitational capture and subsequent system unification. As a result, groups can be important environments for massive galaxy formation. Isolated galaxies which remain in regions with low matter density evolve predominantly under internal process influence. They more rarely experience mergers and can for prolonged time preserve disk structure. However, even under such conditions, medium is not completely neutral. Gradual gas inflow from surrounding space or weak gravitational influences can slowly change system properties. Universe large-scale structure also determines matter inflow directions. Gas and dark matter move along cosmic filaments toward denser nodes. Galaxies located on these filaments can receive additional gas throughout prolonged time. This creates conditions for star formation continuation even in late epochs. However, this mechanism effectiveness depends on galaxy mass and surrounding gas temperature. It is important to note that medium influence is not instantaneous. A galaxy does not change its properties immediately after entering a new environment. Evolution occurs gradually. Gas is lost or heated throughout long time and stellar populations age without sharp transitions. Exactly this slowness complicates distinguishing internal and external evolution factors. Observations show that statistical galaxy properties depend on medium. In dense regions, more frequently are encountered galaxies with old stellar populations and low contemporary activity. In rarefied regions prevail systems with disks and ongoing star formation. However, these tendencies are not absolute. There exist numerous exceptions which indicate complex and multi-factor evolution nature. Science has no single mechanism which would explain all observable dependencies between galaxy properties and their medium. Different processes can act simultaneously or dominate under different conditions. In some cases, the main role is played by gas loss. In others, gravitational disturbances or accretion rate changes. This means that medium should be viewed not as a simple parameter but as a complex of interconnected factors. In quiet reflection, large-scale structure influence can be imagined as a background field within which unfolds galaxy life. This field does not dictate specific events but sets conditions and limitations. Galaxies react to it, gradually changing their behavior without sharp jumps. Thus, medium and universe large-scale structure are an inseparable part of galaxy evolution. They do not replace internal processes and mergers but complement them, creating evolutionary path diversity. Exactly in combination of local and global influences forms the observable galaxy appearance in the contemporary universe. In the course of their development, galaxies gradually change internal process character. Active phases connected with intensive star formation and significant gas inflow with time become rarer. A galaxy does not stop existing and does not transition into a qualitatively different state instantly. This concerns slow aging, within which change ratios between components and dominating evolution mechanisms. Among main activity reduction factors is distinguished gradual decrease of available cold gas. Gas either transforms into stars or heats and becomes less suitable for gravitational collapse. Part of it can be lost into intergalactic space under internal or external process influence. Even without sharp events, this balance slowly shifts toward reduction of reserves capable of maintaining formation of new stars. Galaxies' stellar populations with time age. Young massive stars which determine brightness and energetics have short existence time. After their disappearance in the system remain predominantly smaller mass stars which shine dimmer and live longer. This leads to gradual change of galaxy spectral properties and reduction of its luminosity in shortwave ranges. These changes do not occur sharply. They accumulate throughout billions of years. Galaxy aging is not identical for all systems. Massive galaxies usually pass through active phases earlier and faster transition into low activity state. Less massive systems can preserve stellar formation throughout longer time. This difference is connected both with gravitational potential and with gas inflow history and interactions with surroundings. Internal regulation mechanisms also play a role in activity fading. Stellar and central source feedback influence can heat gas and hinder its cooling. As a result, gas remains present in the galaxy but remains in a state which does not favor new star formation. Such a regime can persist very long and creates an impression of stability, although in physical sense the system continues changing. Observations show that many galaxies in the contemporary universe remain exactly in such a mature state. They contain a significant star quantity but demonstrate low contemporary star formation rates. Their evolution is determined not by appearance of new luminaries but by slow changes in already formed stellar populations. In such systems, galactic structure can persist throughout very prolonged time without substantial rebuildings. It is important to emphasize that activity fading does not mean complete evolution stoppage. Even in galaxies with low star formation level, dynamic processes continue. Stellar orbits gradually change, stellar streams blur, and gas remnants slowly redistribute. These changes occur so slowly that they are difficult to record without prolonged statistical studies. There exist different approaches to explaining why galaxies transition into low activity state. Some models emphasize gas depletion role, others stress medium heating and effective accretion cessation. Contemporary notions are not reduced to one mechanism. Most probably fading is the result of combining several processes which act with different intensity under different conditions. In quiet reflection, galaxy aging can be imagined as very slow quieting. There is no sharp transition between activity and calm. There is only gradual balance shift in which new stars appear more rarely and already existing star roll grows. This process has no clear boundary and is not accompanied by dramatic changes. Thus, aging and activity fading are a natural part of galaxy evolution. They are not a sign of degradation or completion. This is one of possible states to which galaxies come in the result of prolonged growth history, interactions, and internal rebuildings. Exactly in this slowness and change, imperceptibility manifests the characteristic feature of galactic evolution, which significantly exceeds human timescales. Thank you so much for watching. I hope you now have a deeper understanding of how galaxies form, merge, evolve, and age across cosmic time. If you found this video helpful and informative, please give it a thumbs up. It really helps the channel grow and allows me to create more content like this. Don't forget to subscribe and hit that notification bell so you never miss future videos on astronomy, astrophysics, and the wonders of our universe. We have so much more exciting content coming up, including deep dives into black holes, star formation, dark matter mysteries, and the latest discoveries from the James Webb Space Telescope. What aspect of galaxy evolution fascinates you the most? Is it the violent mergers, the mysterious role of dark matter, or perhaps the quiet aging of mature galaxies? Let me know in the comments below. I read every single one and love hearing your thoughts. If you're interested in learning more, check out these related videos on the screen now. And if you really want to support the channel, consider sharing this video with your classmates, students, or anyone passionate about space science. Until next time, keep looking up and stay curious about our incredible universe. See you in the next video.